Next topic, a moving closed path in a static magnetic field. So here closed path means conductor, moving conductor in a static magnetic field. So when a closed path or circuit is moving in a static magnetic field, an EMF is induced in the conductor or closed path. This induced EMF is called dynamically induced EMF. Here closed path is moving and field is stationary. To get a relative motion between them, this action is similar to generator action. Hence the induced EMF is also called as motional induced EMF or generator EMF. Okay, here the closed path is rotating in a static magnetic field. So finally there exists state of change of flux linkages and EMF is induced in a closed path. This EMF is called motional induced EMF or generator EMF. So consider that a charge Q is moved in a magnetic field B bar at a velocity V bar. Then the force on a charge is given by F bar equals to Q into V bar cross B bar. So we know that the electric field intensity E bar equals to F bar by Q. So F bar by Q equals to V bar cross B bar. V bar cross B bar. The induced EMF E equals to closed line integral E bar dot dl bar. Here E bar equals to V bar cross B bar. So induced EMF E equals to closed line integral V bar cross B bar dot dl bar. So this is the induced EMF if conductor is rotating in a magnetic field or closed path is rotating in a magnetic field. The EMF is called dynamically induced EMF or motional induced EMF or generator EMF, and this EMF equation closed line integral V bar cross B bar dot dl bar. So next one, moving a closed path in a time varying field. So the total induced EMF equals to transformer EMF plus motional EMF. Induced EMF equals to formula closed line integral E bar dot dl bar. So this is transformer EMF or statically induced EMF. This is dynamically induced EMF or generated EMF or motional EMF. Okay, if a stationary conductor placed in a time varying magnetic field, then EMF is induced across the conductor. This EMF is called statically induced EMF. Here this term is statically induced EMF. It is also called as transformer EMF. If a rotating conductor or rotating closed path placed in a static magnetic field, an EMF is induced across the conductor. This EMF is called motional induced EMF or dynamically induced EMF or generator EMF. Okay, this term indicates the dynamically induced EMF. If a closed path is rotating in a time varying field, in that case both statically induced EMF and dynamically induced EMF induced across the conductor. In that case the total induced EMF equals to transformer EMF plus generator EMF. Okay, next topic, the modified Ampere circuit law for time varying fields or modified Maxwell's third equation. Okay, for static electric fields, static electromagnetic fields, so according to Ampere circuit law, we can write the Maxwell's third equation, curl of H bar equals to J bar. Okay, del bar cross H bar equals to J bar. This is for static electromagnetic fields or for time invariant fields. So now we have to find this Maxwell's third equation for time varying fields. So take divergence on both sides. So del bar cross H bar equals to del bar dot J bar. So according to vector identity or vector properties, the divergence of curl of any vector equals to 0. So this term equals to 0. So del bar dot J bar equals to 0. Del bar cross H bar equals to del bar dot J bar. So according to vector identity, this term equals to 0. So it equals to 0. So but we know that the continuity equation. So continuity equation formula del bar dot J bar equals to minus dou by dou T of rho V. Okay, let this is equation number 1 and equation 2 and it is equation number 3. So from equations 2 and 3. So equation 2 del bar dot J bar equals to 0. Equation 3 del bar dot J bar equals to minus dou by dou T of rho V. So from these two equations we can write dou rho V by dou T equals to 0. So but for time varying fields, this term value not equals to 0. So for time varying fields, rho V value varying with respect to time. So dou rho V by dou T not equals to 0. So for time varying fields, we have to modify this equation 1. So in order to modify this equation 1 for time varying fields, add one extra term n bar. So equation 1 we can write like this, del bar cross h bar equals to j bar plus n bar. So actually the Maxwell's third equation for constant fields, del bar plus h bar equals to j bar. So but this equation is not satisfied for time varying fields. So why? Because for time varying fields dou rho v by dou t not equals to 0. So to modify this equation, add one extra term n bar. So this is the Maxwell's third equation for time varying fields. So now we have to find the n bar vector. So to find n bar vector, so apply divergence on both sides. So del bar cross h bar equals to del bar dot j bar plus del bar dot n bar. So divergence means dot product with del operator. So divergence of curl of a vector equals to 0. So this term equals to 0, it equals to del bar dot j bar. So from continuity equation, del bar dot j bar equals to minus dou rho v by dou t plus del bar dot n bar. So del bar dot n bar equals to dou by dou t of rho v. So we know that first equation, Maxwell's first equation, divergence of d bar equals to rho v. Divergence of d bar equals to rho v. So del bar dot n bar equals to dou by dou t, rho v equals to divergence of d bar, del bar dot d bar, or del bar dot n bar equals to del bar dot dou by dou t of d bar. So from this equation we can write n bar equals to dou by dou t of d bar. Okay, this is equation number 5. So now substitute equation 5 in equation 4. So we get equation del bar cross h bar equals to j bar plus dou by dou t of d bar, or it equals to jc bar plus jd bar. Del bar plus h bar equals to jc bar plus jd bar. Here first one, this j bar equals to jc bar. Jc bar indicates the conduction current density. So second one jd bar, this is displacement current density. So jc bar is conduction current density denoted by jc bar. Here the current is due to moving charges. The second term is called displacement current density. It is represented by jd bar. This quantity is obtained from time varying electric flux density. So generally some materials are good conductors while some are perfect dielectrics. For good conductors case, it having only conduction current density. In that case, del bar cross h bar equals to jc bar. In dielectric materials, perfect dielectric materials, jc bar equals to 0. In that case, equation becomes del bar cross h bar equals to jd bar. But in some materials which are neither good conductors nor perfect dielectric materials, in that case both conduction current and displacement currents are present. In that case, the total current density equals to j bar equals to conduction current density plus displacement current density. The conduction current density jc bar equals to sigma into e bar. This is from point form of Ohm's law, jc bar equals to sigma into e bar, and displacement current density equals to dou by dou t of d bar. So j bar equals to sigma into e bar plus dou by dou t into d bar equals to epsilon into e bar, or j bar equals to sigma into e bar plus j omega epsilon into e bar. In frequency domain, we can write dou by dou t equals to j omega. In frequency domain, this is the current density expression. Now the ratio of the magnitudes of the conduction current density to displacement current density equals to jc bar by jd bar. Okay, jc bar equals to sigma into e bar. jd bar equals to j omega epsilon into e bar. So modulus of jc bar equals to sigma into e, modulus of jd bar equals to omega epsilon into e. So e cancel, modulus of jc bar by modulus of jd bar equals to sigma by omega epsilon. So if medium is conductor, in case of conductors, sigma by omega epsilon e, omega epsilon greater than 1. In that case, this ratio, okay, modulus of jc bar by jd bar equals to sigma by omega epsilon, this ratio greater than 1. If medium is dielectric material, in that case modulus of jc bar by jd bar equals to sigma by omega epsilon less than 1. Okay, for conductors sigma into e bar. So numerator value high value. So in this case, this value greater than 1. In dielectric material case, denominator displacement current density high value. So this ratio less than 1. Okay, first this is the dynamically induced emf derivation. So next one, total induced emf. If you are moving closed path in a time varying field, in that case total induced emf equals to total induced EMF equals to transformer EMF plus generator EMF or motional EMF. So next, modified Maxwell's third equation. This is Maxwell's third equation for constant magnetic fields. So to modify this equation, add one extra term n bar. Next, find this n bar vector. Here n bar vector equals to 2 by dt of d bar. So finally the Maxwell's third equation, modified Maxwell's third equation, del bar plus h bar equals to jc bar plus jd bar. Here jc bar conduction current density, jd bar displacement current density. So next, these two current densities ratios, jc bar by jd bar. Okay, this is the ratio. So for conductors, this ratio greater than 1. For dielectric materials, this ratio less than 1.